Welcome all to the Waveform Ghostbusters webinar. Today we will hear presentation material from Johnny Hancock. Johnny is a product manager at Agilent Technologies' Oscilloscope Products Division, and he began his career with Hewlett-Packard in 1979 as an embedded hardware designer and holds a patent for digital oscilloscope amplifier calibration. Johnny is currently responsible for worldwide application support activities that promote Agilent's oscilloscopes, and he regularly speaks at technical conferences worldwide. For everyone's comfort, this is a lecture-style meeting. However, you can send questions in writing at any time during the session through the Q&A functionality of the WebEx meeting. We'll do our best to answer your questions during the session, but may come back later if we run out of time. While the answer for your question may be published for others to see, we'll keep your identity private. Please note that this webcast will be recorded, so you can review and share with your colleagues at any time. And with that, I'll hand over to Johnny.
Okay, thank you, Eric. At this point, I'm going to share my PowerPoint slides within PowerPoint. The reason being there are some special graphics that WebEx doesn't support. So anyway, thank you for attending this Waveform Ghostbusters seminar. Let's just take a look at what the agenda is going to be. First of all, we have several examples of what a waveform ghost is, or a ghostly waveform. And we'll show those examples and explain exactly what it is. Then we'll dig into what are some of the characteristics of an oscilloscope that can help reveal these waveform ghosts, including bandwidth and sample rate, memory depth, and waveform update rate. And then we'll go into some scope features that can help you isolate and analyze the ghost, including advanced parametric triggering, a new scope functionality we call InfiniiScan Zone Triggering, segmented memory, and then waveform intensity modulation. So here's the first example of what some people might call a waveform ghost. I've shown signals like this to engineers, and the first thing they say is, there's a waveform ghost. So what is a waveform ghost? It's a flickering waveform. It's an event that is random and infrequent, and sometimes you see it on the scope's display, sometimes you don't. And basically it's just a signal that it's a problem signal. In this case, it's what we call a non-monotonic edge. A signal has a normal rising edge, but occasionally it kind of stalls before going completely up, but it's random and infrequent. This is another example. This is a metastable state, which you might just simply interpret as an infrequent glitch. Metastable state often is caused by a timing violation where you're setting up too close to a setup and hold time. An output begins to switch and then decides, no, there wasn't enough setup time, and then switches back. This is another example. This is just a pretty extreme example of a very infrequent glitch. This is a 1 in a million type event. So on the scope right now, we're just triggering on a rising edge at center screen. It typically triggers on a rising edge of a clock signal, but every 1/1,000,000th occurrence of the clock, there's this infrequent glitch. Now, there's very few scopes on the market today that can actually show you this type of event. This is another example. This is a runt pulse. To define what a runt pulse is a digital pulse stream has a normal high level and a normal logic low level, but occasionally a pulse may never rise to its full output high level or output low level. In this case, we can see both high level runts as well as low level runts. This is an example of a setup and hold violation. And the yellow waveform is channel 1, and that is a clock signal. That's the signal we're triggering on. The green waveform is a data signal. So it's a random serial data pattern, and you can see where the signal is the brightest is where the timing of the switching from highs and lows typically occurs, but occasionally there's a shift, and that's you can tell that it's infrequent because of the intensity of the waveform has a lower intensity. If it was occurring even more infrequently, it might be flickering as opposed to be showing up as a dim waveform. So what are some of the characteristics of a scope that can enhance its ability to capture these things? Now, I ask engineers this question quite often. I'll show them a signal that has an infrequent anomaly, such as a non-monotonic edge or a glitch, and I say, okay, what would help reveal this more reliably? And the answer I get most often is, well, a higher sample rate will improve the scope's probability of capturing it. And this is actually a myth. It's not true. And in fact, there's a major scope vendor that just released an application note that said exactly that. A higher sample rate will improve the scope's probability of capturing intermittent events, and that's not true. A higher sample rate, or sample rate in general, is very closely related to what we call a real-time bandwidth of the scope. And real-time bandwidth and its associated sample rate is a prerequisite for capturing fast and narrow events. It's a prerequisite for capturing signals of any frequency or frequency content, but it will not, but by sampling faster will not improve the probability of capturing something. But we'll go into what is the minimum required bandwidth for capturing normal repetitive signals or infrequent things. The second myth is deeper acquisition memory will improve a scope's probability of capturing events. Now, technically that's true. If you open up, have a deeper memory, capture a wider time span of signals, it does improve the scope's probability of actually capturing it, so long as you can still maintain a high sample rate. However, a deep acquisition on a scope will actually hide any kind of waveform ghost or intermittent events, and it can also decrease the scope's probability of capturing infrequent things, and we'll talk about that a little bit later. So let's first address bandwidth, and this slide we just define what bandwidth is. It is the number one criteria that almost all engineers consider first when selecting a new scope, and I agree that it is the most important criteria. Now, what bandwidth is the frequency of input signals that a scope can continue to show waveforms up until an attenuation of the signal of 3 dB. So what we show in the upper right of this slide is actually a swept frequency response using a input sweep generator. You begin at a low frequency sine wave, and then you sweep up to a higher frequency, and as you get to higher frequencies, you'll see the amplitude of the signals decrease. Where they decrease to 3 dB, which translates to approximately 30% amplitude error, is where a scope's bandwidth is specified. Now, we're showing two different frequency responses here. The red trace represents what's known as a typical Gaussian frequency response, and most scopes 1 gigahertz and below have what's known as a Gaussian frequency response. But some of the higher bandwidth scopes, 1 gigahertz and above, have what's called a maximally flat response, which begins to approach what some people might call a brick wall response. So what is the right bandwidth to select? So here we show an example of two different bandwidth scopes. The scope on the left is a 100 megahertz bandwidth scope. The scope on the right is a 500 megahertz bandwidth scope. The input signal is the same on both of these scopes, in which case it's just a 100 megahertz clock signal. Now you can see two very different responses on the same signal, and the only difference is the bandwidth of the scope. The scope on the left with 100 megahertz bandwidth, trying to capture a 100 megahertz digital clock signal, essentially passes through just the first harmonic of the signal, the fundamental of the signal. Although the 500 megahertz scope passes up to the fifth harmonic, and you see much more detail. So what bandwidth do you need? Well, if you have pure analog applications, this is a rule of thumb that's been around for many, many years. 3 times the highest sine wave frequency is typically sufficient. That's where the frequency response is still in its very flat area of the frequency response curve. But most applications today that people use scopes for are digital applications. And our first rule of thumb is, well, select the scope that's 5 times the highest digital clock rate. That'll allow the scope to capture up to the 5th harmonic, as we're showing in this example. But that's just a rule of thumb. A more accurate bandwidth determination is actually based on the signal edge speeds. In other words, the rise times and the fall times of the fastest signals in your system. Well, let's now take a look at using that criteria if you're going to determine what bandwidth you need. The first step is determine what are the fastest rise and fall times of your devices under test. Now, this may sound like a catch-22. How do I know what they are unless I can connect the scope up to capture them? And what bandwidth scope do I select? Well, you can determine the fastest rise and fall times based on the fastest devices in your system. You can typically go to the data sheets for those devices, whether they're output drivers or whatever, and determine what the fastest rise and fall times are. From that, you can determine the highest signal frequency content, and this is a frequency we call FNI. Now, this comes from some formulas developed by Dr. Howard Johnson, who has written a book very popular called High-Speed Digital Design, a Handbook of Black Magic. And what the NI frequency is, if you look at a fast rising edge and you run an FFT on it, you'll find that there are frequency contents. There'll be a NI in the frequency response where frequencies beyond the NI point fall off sharply and have less significance in determining the reconstruction of that signal. So that's what we call FNI. Some people might call it Fmax. I don't want to call it that because you may confuse that with the maximum frequency related to the Nyquist frequency, and we're going to talk about that in just a few minutes. So if you go back to a particular device specification, some devices will specify those rise times based on a 10% to 90% criteria. More higher speed devices today typically specify the rise times 20 to 80%. So let's take, for example, FNI is, or rise time is specified 1090. Well, then the NI frequency would be 0.5 divided by rise time. So that's the maximum practical frequency within that signal, based purely on the rise time of the signal, not on the clock rate. So once you know the NI frequency, or what you might call the maximum practical frequency, you then can determine what bandwidth do you require for measurement to make accurate measurements. Now, it depends on how much accuracy. If 20% accuracy in making rise time measurements on that signal is sufficient, then you can choose a scope with a bandwidth that's equal to the NI frequency. At the other extreme, if you want extreme accuracy within 3%, then you may want to choose a scope that has, if it's got a Gaussian response, 2 times that NI frequency. If it's a maximally flat response scope, then approximately 1.5 times. So let's just take a look at an example here. Let's say determine the minimum bandwidth of the scope, and let's assume a Gaussian frequency response. So it's got this slower roll-off frequency response to measure signals that have rise times as fast as 500 picoseconds based on a 10 to 90% criteria. The NI frequency would simply be 0.5 divided by 0.5 nanoseconds equals 1 gigahertz. So if you have a limited budget and if 20% accuracy is sufficient, then you could choose a scope with a bandwidth of 1 gigahertz. However, if you need 3% accuracy in making rise and fall time measurements on those signals, then you may want to choose a scope with 2 gigahertz bandwidth. So let's now talk about what sample rate is required to produce that bandwidth in a scope. Now there's 2 trains of thought here, and here I show a cartoon of Professor Smart. He has total trust in Dr. Nyquist and says that all I need is 2 times over the scope's bandwidth. So for example, if you determine you need a 1 gigahertz bandwidth scope, Dr. Smart would say all you need is 2 gigasamples per second. Now Dr. Wise, he doesn't trust Dr. Nyquist, and he says, I want 10 to 20 times over the scope's bandwidth. Now the truth lies somewhere in between these two. Now let's see why. First of all, let's take a look at Nyquist sampling theory. So Dr. Harry Nyquist, along with another gentleman by the name of Dr. Shannon, came up with this sampling theorem. And so what the sampling theorem says, for a limited bandwidth signal, and this is not talking about scope bandwidth, this is talking about limiting the signal frequency input, or the frequency of the input signal, the maximum frequency, the equally spaced sampling frequency, Fs, sampling frequency, must be greater than twice the maximum frequency, Fmax. So Fs must be greater than 2 times Fmax. So this is where Dr. or Professor Wise came up with a 2 over the scope's bandwidth, in order for the signal to be uniquely reconstructed without aliasing. Now the frequency, 2 times Fmax, today is called the Nyquist sampling frequency. Half of that value, Fmax, is sometimes called the Nyquist frequency. What this implies is that there are no frequency components above the Nyquist frequency, and that implies that if that is going to apply to an oscilloscope, the oscilloscope must have an ideal brick wall frequency response. So the scope passes all frequency components with no attenuation up to the Nyquist frequency, and then it cuts off and passes no frequency components beyond. Now this is theoretically impossible with any kind of hardware today. Here we show a typical Gaussian frequency response for a scope. If you specify the bandwidth of the scope at the Nyquist frequency, then there can still be significant frequency components that are passed and sampled that are above the Nyquist frequency, and this will result in aliasing. We'll show an example of that. So here we show an example of a 1 nanosecond wide pulse with very fast edges captured on a 1 gigahertz bandwidth scope, but the scope is only sampling at 2 gigasamples per second. And what you end up seeing is a bunch of uncertainty or wobbling. And what this is, the wobbling or shaking in the waveform, it's aliasing. The scope cannot sample enough information on these fast rising edges. Now most scopes from all vendors today, it's not just Agilent, but other oscilloscope vendors, will limit the bandwidth of the scope to typically, if it's got a Gaussian frequency response, to 1/4 or 1/5. In other words, the sample rate equals the bandwidth times 4. And if you do that, now the possible frequency components that can still be sampled above the Nyquist frequency are significantly minimized. Now a scope with a maximally flat frequency response, which begins to approach the ideal brick wall response, you can limit it to the sampling frequency divided by 2.5. So let's now take a look at the same example, the same 1 nanosecond wide pulse with a 500 picosecond rise time. And so this input test signal that I'm showing right here, this is a repetitive input. This is about the absolute narrowest, the minimum width pulse, and the fastest rise time edge that you can expect to make accurate measurements on. So the screen image on the left, we're showing somewhat of an extreme case. This is a maximally flat response scope, and the sample rate is just 2.5 times the bandwidth. In other words, a 1 gigahertz bandwidth scope, it's sampling at 2.5 gigasamples per second. The waveform on the right is sampling at twice that rate. Now intuitively people would think, well, if the scope is sampling twice as fast, it must be able to capture much more information, but it's actually showing almost the same response. Now visually I can see some differences. The waveform on the left is a little more fuzzy, and what that fuzziness is, it's not noise on the input signal, it is a small amount of aliasing. And if you look at some of the measurements I show RT stands for rise time. We're measuring 580 picoseconds plus or minus 60 picoseconds, and that results in a standard deviation of 24 picoseconds. The scope on the right that's sampling twice as fast, it's slightly more accurate. 500 picosecond input, we measure 550 picoseconds. So we're getting about 10% error, and the standard deviation is about 3 times better than it is with a scope sampling at 2.5 gigasamples per second. But both scopes can capture this very narrow pulse reliably. In this case, it is a repetitive pulse. But both scopes have the same probability if these narrow pulses were random or infrequent. They'd have the same probability. The next example here is a 2 gigahertz bandwidth scope. Now with the 2 gigahertz bandwidth scope, in the example we walked through a little bit earlier, we determined that we could actually get much more accurate results. So this is the same exact input signal, a 1 nanosecond wide pulse with a 500 picosecond rise time. And now you can see the scope on the left sampling at 10 gigasamples per second. So in this case, it's 5 times the bandwidth. We're measuring a rise time of 515 picoseconds. The scope on the right, again, we doubled the sample rate. And intuitively, people think, well, 20 gigs got to be a lot better than 10 gig. You actually get virtually the same result. So sampling at higher and higher and higher sample rates really doesn't improve your probability at all of capturing this. And as far as the accuracy of capturing this, it's very negligible. So if you look at some of the bullets I got down here in the bottom, it's true, higher bandwidth will improve measurement accuracy. Higher sample rate is only slightly improved measurement resolution. So long as we've achieved the minimum required, going higher than that, you get diminishing returns. However, the higher sample rate can produce degraded measurement resolution on some scopes due to sampling noise. Now, we can't go into that one today. It is related to Nyquist, but that's a whole new seminar. Another poor trade-off in going to higher sample rates, it's going to cost you more. Scopes that sample at 20 gig, 40 gig, 60 gigasamples per second, they are extremely expensive. And lastly, higher bandwidth and higher sample rate is actually going to decrease your probability if the pulse is random and infrequent, because scopes that sample at these extreme high sample rates, they're missing a key characteristic that we're going to get to in a few minutes. Now, you may say, if we go back to the example of the scope capturing this narrow pulse at just 2.5 gigasamples per second, you might say, okay, a 1 nanosecond wide pulse with fast edges, it's only sampling at a 400 picosecond time between samples. That doesn't give me much resolution, but all scopes today will automatically run a sin X over X filter, which is based on Nyquist criteria. If you read the Nyquist theorem, he talks about reconstructing a waveform, and that's done with a sin X over X filter. But the sin X over X filter gives you, first of all, it gives you a continuous waveform as opposed to discrete points. It also improves your measurement accuracy. And so the waveform on the right is after sin X over X is run, and now we have data resolution on this particular scope down to 7.5 picoseconds as opposed to not running sin X over X at 400 picosecond resolution. So some people say they don't trust it, but sin X over X reconstruction will always provide improved measurement accuracy and resolution and give you much improved display quality. Now, sometimes there's a trade-off. Most scopes in this class that we're talking about today, we're talking about scopes with bandwidths of 2 gigahertz and below. Sometimes the sin X over X filter on most scopes, it will slow down the waveform update rate, which we're going to get to next. That is the most important criteria. On the scopes that we're showing here today from Agilent, it does not slow down the waveform update rate, and this is because it's performed in a proprietary chip that Agilent has developed called the MegaZoom 4 chip, and it can maintain the scope's full update rate, so it doesn't slow down the update rate at all. Now let's talk about memory depth. That was the second myth I mentioned earlier, that a lot of people say, okay, deeper memory will improve my probability of capturing an infrequent anomaly, and that is true. But let's walk through an example here. The amount of acquisition time that a scope can capture is a function of the scope's memory depth and sample rate. And let's assume you're trying to capture narrow events, so you want to sample at the scope's fastest sample rate. And so the calculation is acquisition time simply equals memory depth divided by sample rate. The problem is here we're showing a 4 megapoint deep memory acquisition on the scope, sampling at 5 gigasamples per second, so we captured 800 microseconds of time. Now there is an anomaly in this record. However, where is it? And what kind of anomaly is it? What you can do with many scopes in this class today is these scopes have automatic search capability where you can search for particular characteristics of signals, such as glitches or slow rise times. But if you don't know that you have some sort of signal anomaly there, how do you know what to search for? In this case, I knew what I input the signal, I captured this, and I knew what to search for. This was one of these metastable state signals, and the scope found 2 of these metastable states, but I had to set up the scope to specifically search for it. So it's what we call a catch-22 situation. This is a movie I think came out back in the 1960s. And so what we mean by a catch-22, how can I, if I don't know that I have a glitch and I don't know what kind of glitch or anomaly it is it a slow rise time or is it a narrow glitch, how do I even know what to search for? Now we get to what I consider the heart of this particular presentation, what will improve the scope probability of capturing infrequent anomalies, and its waveform update rate. Now the inverse, or what's closely tied to waveform update rate, is something we call oscilloscope dead time. Some people call it blind time. All scopes have this what I would call a negative characteristic. So here we show an example, graphic example, 2 acquisitions on a scope. Acquisition number 1, there you can see the display window. Then there's a dead time that what the scope is doing is processing the previous acquisition, acquisition number 1, processing that information so that it can then display it on the scope's display before rearming the scope's triggering to capture the next acquisition. And as we show in this example, during that scope dead time, we actually had 2 anomalies, but the scope totally missed it. And this particular graphic is actually a pretty extreme exaggeration of dead time. Dead times that can actually be orders of magnitude longer than oscilloscope display time. And so if you have something very random or infrequent, it's more likely to occur during the scope's dead time or processing time as opposed to occurring during the scope's acquisition time. Here we show now a scope that has decreased dead time, and now we missed 1 anomaly, but we captured 1 anomaly. So decreasing scope dead time, which will increase, or decreasing dead time will increase waveform update rate, will improve the scope's probability of capturing an infrequent event. So here we show an example, the one I showed earlier, of the non-monotonic edge, very infrequent signal that sometimes has a slow rising edge. The waveform display on the left, we've set up the scope, intentionally slowed down its update rate down to 1,000 waveforms per second, versus the scope on the right is updating at 300,000 waveforms per second. The scope on the left totally misses and does not show you that you have a signal problem. The scope on the right does show you that you have a signal problem. So once you realize that you do have signal problems, the scope, let's assume it has a waveform update rate that is sufficiently fast, I often ask people, okay, now what do you want to do? And the right answer, and I usually get the right answer, even if I'm talking to smart engineers, they say, well, I want to isolate it. And I say, well, how do you isolate it? I need to trigger on it. I want to trigger uniquely on the problem signal. Now, many scopes in this class have advanced triggering capabilities. The trigger mode that most people often use is just edge triggering. But if you look at the screen on the right, here we show a menu that shows the wide variety selection of various trigger modes. You can see up at the top is edge triggering mode, then edge, pulse width, pattern. When I ask people on this non-monotonic edge which one you select, actually most people say pulse width trigger. The right answer is rise and fall time trigger. But the issue is you must know what the normal rise times are in order to set up a timing criteria in order to trigger uniquely on a slower rise time, which this non-monotonic edge is a slower rise time. And here we show the results of after you've set it up. In this case, we set it up to trigger on a rising edge. We had to set up an upper and lower threshold level. And then we said only if the rising edge is greater than 165 nanoseconds. And so now we've uniquely been able to establish oscilloscope triggering to uniquely trigger on the slower rising edge. So we only capture the problem signal and don't capture the good signals. Once you've been able to do that, you've isolated the problem signal, now you can use other channels of the scope to perhaps probe other signals that may be interfering with this signal, maybe synchronous to it. Maybe there's a power surge or something else that's happening in the system that is happening synchronous to the problem signal. But there's actually an easier way. Agilent's latest oscilloscope, the 4000X series, we call it the InfiniiVision series, has something new we call InfiniiScan Zone Triggering. Now, when we went through the process of actually setting up the scope to trigger on the slow falling edge, to be honest with you, it is not that easy. I mentioned earlier, most people just simply use rising edge trigger. Most engineers are not oscilloscope experts. And setting up the rise time trigger took several steps. With zone qualified trigger, all you need to do is draw a box on the scope screen using the scope's touch screen. It's a capacitive touch screen, or you could use a mouse, and you just draw a box only in the area of the problem signal, and the scope will lock in on it. So if you can see it, the scope's update rate shows you the trigger problem or the signal problem, zone trigger can catch it. Here we show the example of the metastable state. Again, draw a box in the area of just that metastable state or that infrequent glitch, the scope locks in on it. This is the 1 in a million glitch that we showed earlier. Again, draw a box in the area of just the glitch, not the normal part of the waveform. The scope locks in on it, and now, again, you can correlate it to other signals, find out what's causing it. This is the example of the runt pulse. Now, in this case, you look at the waveform on the right. We're just triggering on just rising edge trigger. There are runt pulses that are narrow, and there are runt pulses that are wide. The zone trigger capability, actually, you can draw two different zones. So in this example, we're showing zone 1 on top of the narrow pulse, zone 2 on top of the wider runt pulse, and we define the second zone as a do not intersect zone. In this case, the scope locks in on just the narrower runt pulse, and here we show it locking in on just the wider runt pulse. So the zone triggering capability, what its real value is ease of use. We could have set up all these trigger conditions using the advanced parametric triggering, but visual triggering, drawing boxes in the area of the problem signals, is much easier and much more intuitive. And here's the example of the setup and hold time violation. So where the signals are more dim, they're happening infrequently over here on the left. This is a setup time violation. Again, draw the zone in this area, and then we lock in on just the bad signals or the problem signals. Now let's go back and talk about memory depth again. Now remember, we mentioned that the maximum acquisition time that a scope can capture while using its maximum sample rate is the memory depth divided by the sample rate. So if we use the example for the specific scope for all the waveforms that I've captured in this particular seminar, it has a memory depth of 4 million points and a maximum sample rate of 5 gigasamples per second. So the maximum time that the scope can capture while sampling at its fastest rate is 800 microseconds. So in this case, we show an example of the input signal or some narrow pulses that are occurring 400 microseconds apart. This means we are limited to only capturing 2 pulses. But what if I wanted to capture more than 2? Well, you could change the time base. You could open it up and say go to 1 millisecond per division, for example, and that would allow the scope to capture 10 milliseconds of time. The problem is all scopes, once you exceed that maximum acquisition time that they can capture at the maximum sample rate, they'll automatically reduce the sample rate, which means you could lose resolution on capturing these narrow pulses. The solution is segmented memory acquisition, which is available on many scopes today. It goes by different names. Agilent calls it segmented memory. I think some other vendors call it fast frame or sequence mode or history mode. And what it does is selectively captures more waveform data by only capturing narrow windows around each event that you want to capture. Now here we show the events with nothing in between the events. This could be a complex digital pulse stream, and we'll show a real example of that in a minute. And you uniquely set up a trigger condition, and you can set it up to capture just the event based on the trigger condition, ignore everything else. So in this case, we show an example of capturing 400 milliseconds with the scope still sampling at its fastest rate. But what the scope doesn't do is it doesn't capture anything in between. It only captures the events of interest. But in this case, I've been able to capture 1,000 of them. Now, you could compute what would the equivalent memory be if I didn't have segmented memory, if I just simply had very deep memory to capture 400 milliseconds of time at 5 gigasamples per second. That would require 2 gigasamples or 2 gigabytes of memory. Now, there are no scopes on the market today that have 2 gigabytes of memory, and if there was, it would be very expensive. The deepest memory available today on any oscilloscope, and it's actually available from Agilent, is 1 gigabyte. So here we show a real example. This is another example of the metastable state. You take a look at the waveform on the left. You can see what appears to be a random and infrequent glitch occurring near center screen. So step 1, we're triggering on just any rising edge of the signal, and it's randomly capturing these narrow glitches at center screen. Step 2 would be to set up the scope to uniquely trigger on that condition, which we can use the scope's advanced parametric triggering, in which case down here in the bottom I've set it up to trigger on a pulse width, positive pulse, if it's less than 50 nanoseconds. So now the scope on the right is only triggering on these narrow pulses at center screen. And then using segmented memory, we could capture 1,000 consecutive occurrences. And then I'm able to go back and review each occurrence as well as view the time of each occurrence relative to the very first occurrence, the first glitch it captured. In this particular example, we captured 1,000 events over nearly a 300-second time span. Now, we didn't capture anything in between. We just captured the problem signal. The equivalent memory, if I was to use continuous acquisition, if I didn't have segmented memory, in this case would be 1.5 terabytes of memory. Again, this is way beyond the capability of any scope on the market today, but it can be done using segmented memory. The last topic we're going to talk about here today that is another tool that's available in many oscilloscopes today is waveform intensity modulation that can reveal some statistical information about your waveforms. Now, when digital scopes first came on the market about 20 to 25 years ago, there was no intensity modulation. Whatever they captured, they displayed all at the same intensity. For some of you that have been around for 25, 30 years, such as myself, may have used older analog oscilloscopes. This is a natural phenomena of an older analog oscilloscope. They display waveforms that occur more frequently, brighter, and signals that they capture and sweep across screen. If they're more infrequent, they display them dimmer. So it gives you a intuitive visual feedback for the relative frequency of occurrences of signals. So in this particular example, you can see up at the top of the waveform where it's bright, you can see the various shades. That gives you some information about the noise, and then the infrequent signals are very dim. Agilent's MegaZoom 4 technology, which is available in this particular scope, it supplies up to 64 levels of intensity modulation, and that is actually more than the eye can detect. So if you come across a scope that has 256 levels, and we have some that have that, you can't see 256 levels of intensity. So 64 is more than enough. And to be honest, 16 levels of intensity is sufficient. So let's review what we've learned today before we go to our Q&A. Real-time bandwidth is a prerequisite for capturing not only infrequent signal anomalies, which we've been calling waveform ghost, but it's also a prerequisite for whatever signals you need to capture. Sampling faster does not improve the scope's probability of capturing these infrequent things. Deep memory will actually hide waveform ghosts. As we showed, you capture a deep memory record, there may be a glitch there, but you can't see it. The key, which I've got underlined here, fast waveform update rates are the key to improving a scope's probability of capturing waveform ghost. In my opinion, the number one criteria is bandwidth and sample rate. Number two criteria, most important criteria of any scope, in my opinion, is waveform update rate if you're trying to debug and try to solve problems. Advanced parametric triggering, that'll help you isolate ghosts, but this new zone trigger that I showed you actually achieves much of the same thing as advanced parametric triggering, but it makes it much easier and it's much quicker to isolate and then zero in on perhaps what's causing these things. Segmented memory, we showed, allows your scope to capture more significant information without capturing the insignificant information. Capture what's important, not what's important. And waveform intensity gives you a relative feel for how often things occur. Now, we have a lot of technical resources. If you're interested, you can download from Agilent Technologies website. Now, if you just go to agilent.com, you may have a little bit of problem finding these particular application notes, but I've listed a URL down here at the bottom, and you can just simply insert the publication number in place of wherever I've got the XXXs. The application note that applies most specifically to what I'm talking about here today is the third one here, called Oscilloscope Waveform Update Rate Determines Probability of Capturing Elusive Events. And the next one down, Synchronizing on Infrequent Anomalies and Complex Signals Using InfiniiScan Zone Trigger. Now, we also have several videos. I've listed the ones that I think are most applicable to what we've talked about today. They're available on YouTube. You could just simply go to YouTube and put in their little search box there some of the keywords. You might say zone trigger, and that particular video would probably pop up. I'm not going to spend a lot of time trying to sell you on our specific scopes, but this gives you an overview of the three families of scopes that we have within the InfiniiVision X series. We have scopes in this series range from 70 megahertz bandwidth up to 1 gigahertz bandwidth. All of the screenshots that I showed today were from the 4000X series, which is a new series we just introduced in November. Out of these three scopes, the 2000, 3000, 4000, the 4000 is the only one that has the InfiniiScan Zone Triggering capability. Also, what I might mention about this family of scopes, virtually everything is upgradable. So if you have a limited budget, You can begin with a lower bandwidth scope, say a 200 megahertz bandwidth scope in the 4000 series. You could later upgrade to 350 or 500 or 1 gig or 1.5 gigahertz. You can add serial bus options later. You can add various options. You can even add the digital input channels, what we call an MSO. Virtually everything is upgradable. The only thing that's not upgradable is the number of analog input channels. So at this time, I'm going to turn it back over to Eric and see if we have any questions here today that I can answer for you.
Okay, thank you, Johnny. Let's have a look at the questions. So actually, if you still have any questions and not posted yet in the Q&A section, please do so, and we'll aim to answer them still now in the Q&A section. But we already had a few coming in. So let me start with the first one, Johnny. So how is it possible to reduce a scope's update rate?
Okay, I did show one example where I showed an example of the scope updating at 1,000 waveforms per second, and another example updating at its maximum rate for that particular setup condition. The way I did it in that example is most scopes on the market today have what's called a trigger hold-off capability. The primary purpose of trigger hold-off is to trigger on a burst of signal, so the scope can sink in on, say, the first pulse of a burst and not randomly trigger on the second, third, fourth, 100th, whatever. That's the primary purpose of trigger hold-off. But if you wanted to, for some reason, I don't know why, if you wanted to slow down your scope's update rate, if you put in a trigger hold-off of 1 millisecond, then the scope would trigger on an event, then it would disarm triggering for 1 millisecond before it rearmed the scope's triggering, in which case the maximum rearm rate would be 1 millisecond or 1,000 waveforms per second.
Okay, thank you. Next question. What can I do on a scope to maximize update rate or reduce dead time?
Well, a lot of scopes have trade-offs. If you look at different vendors' oscilloscopes data sheets, their specifications, they all, including Agilent, will highlight the best case. There's a lot of factors in a scope that are going to affect waveform update rate. The biggest one is where you set your time-based range. If you set your time-based range, let's say, at 1 millisecond per division, that means it's going to capture 10 milliseconds across screen. You got an acquisition time of 10 milliseconds. And even if the scope had 0 dead time, the absolute maximum update rate the scope's going to have at that time-based setting is 100 waveforms per second. So setting your time-based range is one thing. Also, most scopes, it depends on what you have turned on a scope. Do you have complex measurements, FFT turned on? Those type of things will typically slow down a scope's update rate. Do you have serial decoding turned on? Do you have the MSO digital channels turned on? That will typically slow down a waveform update rate. Some scopes you can manually turn off sin X over X to improve. On Agilent's InfiniiVision series scopes, none of these factors affect the scope's waveform update rate. It's all performed in this MegaZoom 4 hardware chip that we have, this ASIC chip. And you can turn on serial decode, you can turn on measurements. And none of these things degrade the scope's update rate or increase the scope's dead time. The one thing that does, though, is if you, again, you open up the time base to capture a long period of time, that is going to naturally slow down your update rate.
Thank you, Johnny. Next question, what is the rearm time for segmented mode?
Okay, on the scopes that I showed here today on our InfiniiVision 3000 and 4000 series oscilloscopes, the minimum rearm time for those scopes is 1 microsecond.
Thank you. Also question, how is it possible to achieve 1 million waveforms per second if the scope display is updated just at 60 hertz?
Well, that's a good question. Now, all scopes today, most scopes, they have a flat panel LCD type display, and they have a refresh rate typically of 60 hertz. So they refresh every approximately 17 milliseconds. So how can we put 1 million waveforms on a second if the scope's refresh is only 17 milliseconds? Well, our scopes actually have a minimum persistence, and that is the refresh rate of the scope. So for each refresh of the scope's display every 17 milliseconds, there can be thousands of waveforms on screen.
Okay, thank you. Also a good question here. So how can I know what the scope's waveform update rate actually really is?
Well, as I mentioned earlier, there's a lot of variables that determine the scope's waveform update rate. Now, you can just look in a vendor's data sheet to see what the best case is. Not all, but most vendors specify what the best case is. In the case of this series of scopes, it's 1 million waveforms per second. But most scopes in this class have a trigger output signal, usually on the back panel of the scope. You can connect a BNC to the trigger output signal, then run it into a counter or into another oscilloscope and simply measure the frequency of that trigger output signal.
Okay, thank you. And a last question, are there any disadvantages of fast waveform update rates? Any disadvantages?
In my opinion, there are no disadvantages. However, we have had some input from our customers. One phenomenon that you will see on a scope that has an extremely fast update rate is some customers say, your waveforms look fuzzier, they look more noisy, and they think our scopes have more noise. And what the fast waveform update rate is doing is actually capturing more noise. Noise, if it's random, if it's Gaussian, which is a typical white noise, will have extremes that happen more infrequently. They'll have extremes of positive peak noise, negative peak noise that happens less frequently than the 1 sigma type noise. And if a scope has a fast waveform update rate, it's going to pick up those extremes extremely fast, whereas a scope with a slow update rate is not going to show you those extremes. So if you don't want to see the noise that's really there, you can use a method I talked about earlier of intentionally slowing down your scope's waveform update rate. But in my opinion, I want to see what's there, even if it's extremes that are not pleasing to the eye. At least it's showing me what's really there. The scopes that are updating slower are masking or they are hiding what's really there.
Okay, thank you, Johnny, for presenting and going through the questions. So if there's any other questions after the event or want to ask these offline, don't hesitate to contact us on the address provided. In a few seconds' time, we will close the webcast. An evaluation form will pop up on your screen, and we do appreciate your feedback. Thank you again for your attendance.